Now we shall consider the last article from this chapter, which is the Diophantine equation, and it is ax plus by is equal to c, where a, b, c, x, y are all integers. And in this chapter or in this paper, we are studying integers only. We have a relation for this. Diophantus is name of mathematician who studied this type of equations. And theorem related to this is the linear Diophantine equation, this first degree equation, and therefore it is called linear. Ax plus by is equal to c has a solution if and only if d divides c, where d is the GCD of these two integers a and b. So that is the first part of the theorem. When this equation has a solution and when it does not has a solution, the condition is we have to consider the greatest common divisor of a and b, and if it is d, and if that d divides c, or c must be multiple of b, then the solution exists, otherwise not. And second part is about the solution. If x naught y naught is any particular solution of this equation, then all other solutions are given by this relation in terms of x naught and y naught. The equation has infinitely many solutions, because this is only single equation in two variables, and all solutions are given by x is equal to x naught, known solution, plus b by d times t, and y is equal to y naught minus a by d into t, where t is arbitrary integer, means t is any integer, positive, negative, including 0 also. So this is the theorem. Now we shall consider the proof. We will consider again the equation. The Diophantine equation is ax plus b into y is equal to c, and we shall suppose this as 1. Next we shall consider the GCD of AB is equal to d. Let greatest common divisor of a and b is equal to d, and therefore d divides a and d divides b. And by the earlier result, we can write this d divides a and d divides b. So therefore there exist relatively prime integers r and s, such that a is equal to d into r and b is equal to d into s. By definition of divisibility, a is equal to d into r and b is equal to d into s. Now what we shall have to show that this solution exists. If we have b is equal to GCD of AB and d divides c, then the solution exists. That we have to show. So for this purpose we shall consider next as, suppose equation 1 has solution x naught and y naught, then we will show d divides c. Suppose x naught y naught. X naught y naught is solution of this equation, means x naught y naught, values of x and y as x naught y naught satisfies this equation, and therefore we have c is equal to, I should write this side as the left side and right side as ax by, where x is x naught, y is y naught is the solution, and therefore c is equal to ax naught plus by naught. Now in this we shall use the value of a and b from, suppose this as second relation, or therefore c is equal to a is d into r x naught plus b is ds into y naught. And now we can take d common. So this is c d into rx naught plus s y naught. And clearly this shows that c is multiple of d, or d divides c. So this shows that, and so one way we have proved there is solution, then we have d divides c. Now conversely we shall suppose d divides c, and then we shall show there is a solution, because theorem has two parts, if and only if part, two-way relation we have to show. Conversely suppose d divides c, and therefore we can write c as d into t for some integer t. C is equal to dt by definition of divisibility. We can write c as multiple of d, and thus c is equal to dt. Then we will consider the greatest common divisor also. See, suppose d is equal to the GCD of AB, which can be written as a x naught, combination of x naught and y naught. Also, d is equal to GCD of AB, and therefore d can be written as d is equal to ax naught plus by naught for some integers x naught and y naught. This is theorem 3. Now we will consider c. C is equal to d into t. And in that we will use the value of d. Now c is d into t, and this is, what is d is ax naught plus by naught times t. So this equation can be written as a x naught into t plus b y naught into t. And now what this shows as this equation, ax plus by is equal to c. It is of this type, and it shows that it has the solution. This equation has solution as x naught t and y as y naught t. So from equation 1 this shows that or this may be written as a x naught t plus b y naught into t is equal to c. So this shows that x naught t and y naught t is a solution because it satisfies this equation. Ax plus by is equal to c is a solution of equation 1. And thus we have proved the first part. This proves the first part of the theorem. That is, if it has solution, then d divides c, and conversely, if d divides, we have suppose d divides c, and then we have proved equation 1 has a solution. That completes the first part. And the second part now is, if x naught y naught is one solution, any particular solution of this equation, then all other solutions are given in terms of this x naught y naught, like this. So that is the second part. Now to prove the second part, suppose second part of the theorem. Let one solution we know is x naught y naught. Let x naught y naught be known solution, and let x dash y dash be any other solution. Then from 1 we have 1 means this equation. See, this is equation 1. So both are solutions. X naught y naught is solution, x dash y dash is also solution. So therefore both these pair of integers satisfy equation 1, and therefore we have from 1 as, say, ax naught plus by naught, which is c, is equal to, and x dash y dash is also solution, that is ax dash plus by dash. Or from this we can consider a into bracket. We take this x naught on that side, x dash minus x naught is equal to b, and we take y dash on this side, y naught minus y dash. So this is a relation that we will have. Now what we shall consider is GCD of a and b is d. And we have the values of a as dr and b as ds. So we will use that value. GCD of AB is d, and therefore d divides a, d divides b, and therefore a is equal to dr and b is equal to ds for some relatively prime integers r and s. R and S are relatively prime. So this part we have written earlier, these equations we have written earlier, and we may refer that as 2. So put that value here. So therefore, so we have a into x naught, x dash minus x naught. A is dr. Therefore we have dr into x dash minus x naught is equal to ds into y dash, y naught minus y dash. And now we see d is common on both sides, can be divided, and therefore the equation becomes, or the equation remains as r x dash minus x naught is equal to s y naught minus y dash. And what this shows that r divides s into y naught minus y dash, because this has a r as a factor. So therefore this shows that, or this implies, r divides s into y naught minus y dash. Now but we have written r and s are relatively prime, and therefore r does not divide s, but r does not divide s. And by Euclid's lemma, if r does not divide s, then r must divide y naught minus y dash. You may refer this Euclid's lemma, r must divide y naught minus y dash, and therefore this implies this is multiple, y naught minus y dash is multiple of r into t for some integer t. And from that we can write y naught, y dash s. Therefore y dash from that will be, so I shall write here, the first part we have to do. See, from that y dash is, take y dash on that side and rt on this side. Therefore, y dash will be y naught minus rt. And what is r? From this relation, you see, r is a divided by b, and thus we can write a by b times t, or we may suppose this by this relation by 2 and this is by 2. And now we have this value y naught minus y dash is equal to rt. Put it here in this relation 3. Also from 3, we have r x dash minus x naught is equal to s, and y dash y naught minus y dash, which is rt, sr. R is common on both sides. We divide both sides by r, and what we get is x dash minus x naught is equal to r. And again from this we can get the relation for x dash. X dash is equal to x naught plus r. And again this is x naught plus what is r from this relation will be a by d. And see, we must have this as in terms of s. So r is cancelled. Correct this. R is cancelled, so s remains here. And therefore x dash minus x naught is st. And therefore x dash is x naught plus st. And now what is the value of s from second? It is b divided by d. So it is b by d times by. And thus we have, now we shall denote the solutions in general, other solutions by x and y. So thus we have x is equal to x naught plus b by d into t, and y is equal to here. Y dash means y. The solution is denoted by now changing notation. Solution y. Y is equal to y naught minus a by d into t. And hence the other solutions, all other solutions are, or we may say all other solutions are given by x and y, where t is arbitrary integer, means t can take any integral value, and this proves the theorem about Diophantine equation. Now next time we shall consider an example about this Diophantine equation. Thank you.